All right, welcome to the first Zoom for MAT266 B session. I generally have one of these once a week, usually on Sunday, but it might vary depending on when testing is taking place. This is just like office hours. It, it's basically question driven. You tell me what you want to look at, and I can work it out for you. I've got a camera here I can set up. I am recording this, so it'll be available so you can view it later if you want. You can leave at any time. You can come back at any time. You don't have to participate. You can just sit and watch if that's your preference. I do have Infinity up, ready to go if anybody wants to ask a question from that. And that's pretty much how it is. So it's pretty casual. So I see I've got a lot of people tonight. I've got, looks like 11 people. That's pretty good. I'm happy about that. Who would like to start us off? Anybody have any burning homework questions that they want to look at? Go ahead and just jump in.
Hello, can you hear me?
Robert, can you repeat that, please?
Can you hear me?
I can now, yes.
Okay. I didn't have a homework question. I just wanted to double check with someone involving the honor lock upload or getting the setup part one.
Yeah.
I've completed it here, but I don't know if I've screwed up or not, but I went through and completed it, did not see a turn-in test, so I exited out of honor lock. And then I guess like when I was trying to go to Affinity to do the part two there, it just kept going back to do part one. So I went through the process of getting back in and it put me back into part one with like
Uh,
minutes left. And then all of a sudden I did notice the turn-in test
oh, I see
above it and
it.
I
No,
didn't
you're
get it
fine.
all. Okay, that's want to make sure I didn't accidentally
I just
screw
haven't
that up or
gotten to
something.
it yet.
Well, I just
No.
did it like half hour ago, so
All right.
I
Yeah,
was
I
just concerned
usually I've
about.
been hitting these about once a day. So yeah, you're fine.
Okay, thank you,
Um,
sir.
yeah. I just check in about once a day on those. All right. Anybody have any homework questions? Any integrals? Want to, Erica?
I'm gonna put a list of the questions that I had that I kind of wanted to see went over in the chat. I'm in the hospital right now visiting my
Okay.
aunt, so I can't stay on. Like I'm gonna be here, but I can't stay on and talk because there's
Oh,
gonna be like people
that would be
walking
fun.
through.
You'll put it in the
I'm just
chat.
gonna. Mm-hmm.
Okay.
So
Yeah.
I have them.
Okay.
Okay, I
So
apologize.
question one. Uh, I'm sorry. Question 19 on 5.5. Let's start with that one. Yeah, you got a lot up there. I don't know if I'll get through all of them.
Yeah, that's okay. I try to pick like ones that have like from different aspects of like there's a lot from 6.2 because I think 6.2 is the most difficult. And then I think the other ones are basically I think the issue that I was having was when you have the when you're getting the integral and you're finding the indefinite integral, I'm having trouble when then I end up with like 1 over u times du, and then it ends up like recognizing when sine over cosine is the ln of sine or what, that's the part I think that most of these are focusing on.
Let me tell you what. I'll start off with question 19 from 5.5. And then you said you wanted to look at one from 6.2.
Oh, you can. Any of those are good.
All right.
Any of them.
I'll
Yeah,
tell
and
you what.
if
I'll
anybody
do.
else has stuff to go through, then you can definitely like jump to theirs. Like we definitely don't have to go through all the ones that I have up there. I just that was the list that I had written down, and I hadn't been able to get home because I'm still in the hospital. So I was like, I'll just put them in the chat, and then if there's ever dead time, then there's a list of possible ones to go over.
All right. I'll tell you what. I've got 19 up here. I'm going to share the screen. It's this one, right? Now, your numbers might vary slightly, but it's the same structure. Is this the one? Okay. Let's take a look at this one. So it's the integral of 9x plus 1 on top, x squared plus 1 on the bottom. I'm gonna switch the screen here a little bit. I'm gonna go to my overhead. I'm gonna go to the there we go. So one thing you can do on a question like this is split it up into two parts, the numerator. And this particular one, you just got to kind of know these forms. This is not factorable. X squared plus 1 is irreducible over the reals. However, this is a form, you probably would have seen this at the very end of Calc 1. This is going to be a natural log form. This one's going to be an arctan form. Okay. In the first case, the 9 is just a spectator. I'll pull it out front. It doesn't affect the second one at all, so I'll just write it as a separate one, all dx. On this one right here, you notice they look similar. That's the thing. They look a lot alike, but they're totally different forms, because on this one we can let u equal x squared plus 1. Du is then 2x dx. I actually have a dx right there. I have all the structures good. I've got the x in the dx. So if I just kind of gently write in a 2 and a 1/2 on the outside, then I can work it out as a simple ln integral. It's going to be du over u. So 9/2 ln of u. And I'll just write it right here, 9/2 ln of x squared plus 1. Okay. This one right here is just a straight application of the arctan. It's actually just the arctan of x. Now, one of the ones that a form that you want to know is the general arctan. So if you have 1 over x squared plus a squared, this one's always going to be 1 over a arctan x over a. This is a form you probably should memorize. Okay. Did that help with that one?
Yeah, I had the arctan memorized, but I didn't break up the equation. So I think that was my problem, was I was trying to do like 9x plus 1 over, and I couldn't figure out how to get it into there. And then I was able to I was able to follow the example to get to the final answer, but I didn't know why. So that was very helpful. Thank you.
Okay. Well, that's a trick you can use. You can always split a numerator at any sign. In this case, it worked out well for us. Let me take a look at one from I'm just gonna pull one from 6-2. I'll tell you what, number 6, why not, right? So I'm gonna go to 6-2, and I have no idea what that one is, so I'm gonna be surprised just like everybody else. Oh, come on, infinity. So number 6, oh, it's a secant tangent. All right. Give me a second here. I'm gonna share. So it's this guy right here. It's evaluate the integrals, secant squared, tan ninth. All right. Let's see what that one's all about. Oops, my bad. Hold on. Let me rewrite that. It's going to be secant x, secant squared, tan to the ninth x dx. All right. A couple ways to approach this one. I'm looking at this. Actually, you know what? This might just be a good old-fashioned UDU. You want to memorize like the derivative of the tangent is secant squared. So this one's it looks like it's going to be a UDU. The derivative of secant, we should probably know that one, is secant tangent. Now this one works out just dandy because I've already got a secant squared. So if I let u be tan x, then du is secant squared x, and it's already good to go. I've got the secant squared, so I'll just these two guys blob into the du. This is just going to be u right here. So really what I have here is just u to the ninth du. So that's 1/10 u to the 10th. And then I just make the replacement like that. All right, well, that one worked out kind of nice. That was a little unexpected. I was expecting something rougher. But on these questions, I'll tell you what, I'm going to share the screen again because one of the things you're learning about working with these trig integrals is just trying to keep track of what identities and what derivative forms you have handy. So for example, on this one, number 7 with secant to the fourth, I might split that up as secant squared squared, and then take the one of them as secant squared and rewrite it in terms of tangent. I'll tell you what, let's take a look at that one. I'm just, as an example, the way I view these problems is these types of questions are really good at just really kind of pinning down a lot of your trig and algebra. That's really the value of these questions. So I'm going to take a look at this one too, since I've had it up there. Again, it's just like a puzzle. You're trying to break into the puzzle. And I see the secant to the fourth, and I think to myself, I bet you if I did secant squared, t to the t over 8, and then secant squared t to the t over 8, um, then I can take one of them. I'll take the second guy right here and write it in terms of the tangent. And I always, so what I do just over here, sine squared plus cos squared is 1. If I divide through by cos squared, I get tan squared plus 1 is secant squared. So it's going to be tan squared t to the 8, t over 8 plus 1. And so suddenly this integral is secant squared t over 8 tan squared t over 8 plus, and then I'm distributing secant squared t over 8 blah, 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 dx. Okay. And this one will work out. This first one here is actually just a lot like the one we just did, except it's only in the second power. We got that t over 8 to deal with. It's going to be 1/3 tan cubed t over 8. Now, I'm kind of skipping some steps here, but if u is t over 8, then du is going to be 1 over 8. So I would have to temporarily just kind of write in a 1 over 8 on the outside and an 8 on the inside and an 8 on the outside. So actually that becomes an 8/3. And I always recommend to you guys to take your derivatives to check. Okay. So, and then this one right here will just be kind of the same thing. It'll just be 8 tangent t over 8. Okay. Anyway, on these types of questions, just try splitting them up, try seeing if the Pythagorean identities can be invoked, see what other identities can be invoked. They will work. All of them will work. You just need to figure out how to break into it. Okay. Um, I'll tell you what. Would anybody else like to jump in with a question, or if not, I can always go over some more of these, but if anybody else has a burning question, please, jump in.
Yes, sir. I do have a question.
Uh-huh.
So I was a little bit confused on the indefinite integrals. Or no. Yeah, when you do the substitution rule.
right?
Um, so I know you want to pick the U to be the hardest question or the hardest equation. And then du is just the derivative of it.
Well, not
Or
necessarily, I
is
wouldn't
it?
call it the hardest. You need to, you're looking at the integrands and you're looking for a structure. So for example, if you saw x sine x squared dx, the u du substitution rule is actually the chain rule performed in reverse. So you got to be thinking chain rule. When you take the derivative of something and you use the chain rule, you end up actually adding factors to your answer. The derivative is kind of a bigger function, if you will. So if I took the derivative, actually, let's just work this one out. I would look at this and I would say, you know what? This x looks like the structure for the derivative of x squared. So I would let u equal x squared, du would be 2x dx. And as long as I've got the structure in place, I'm good to go. Constants can always just be kind of tucked in. Okay. So suddenly I just have 1/2 sine of u du. That's just going to be negative 1/2 cos u, which is x squared. Okay, that would be the answer. So now, if I were to check this by taking the derivative of cosine is negative sine, and it's going to be cosine x squared, so negative sine x squared. And then I have to do the chain rule. That's 2x. And check this out. The 2's cancel, the negatives cancel, and we're right back to the original. We got x sine x squared. And you'll notice that by taking the derivative of this extra factor appeared because of the chain rule. So that's kind of the idea. You're trying to look at the structure of the integrand and trying to identify which one it matches best. Like the first one that was asked a while ago, I'll just bring it right back up. Um, there we go, found it. This one right here, 9x on top, x squared plus 1 on the bottom. If you the 9 can be ignored, just moved out in front. If you recognize that the x here gives you the structure of the derivative of x squared plus 1, if you let this be your u, then the derivative is just 2x. I have the x. I can pop in a 2 and balance it with 1/2. That's the idea. You're kind of looking at the integrand to get a feel for which rule applies. I will admit, and this is what you're going to experience, they look a lot alike. Okay. So it's not, sometimes it's not that obvious. You have to try things. And one of the best ways to learn is just to try. And you may end up failing a few times, but at least you know. All right. You know, if it's not one style, it's got to be another. There's only so many choices you have. So, all right.
Yes, sir.
Did that help you?
Yes, sir. It did.
A lot of this just takes a lot of practice.
Yes, sir. Yeah, I think. Yeah, when you have the two in the front, 2x of the integral. So how do you get the 1/2? I guess whenever you do
I wrote
your
in the
the
two.
du.
I need a two there to make this work. There wasn't a two there originally. Okay. If I say u is x squared, du is then 2x dx, I need a two. I can put in constants at will. This is all just multiplication. What's 2 times 1/2? It's going
Just
to be
one.
1. So I haven't really changed the value of the integral, but I have given myself stuff to play with. I need a 2 there. That's what's driving this whole thing. For this thing to work, I got to
Oh,
have
I
a
see.
2 there. So I put a 1/2 to balance it. The 1/2 survives. The 2 actually just gets blobbed in with the dx. The
Hmm.
dx and the 2x make your du.
Okay, I see.
All right.
And then What about integration by parts when you have to actually do it twice? So what determines like you
Do you have a
have to
question
do
in
it
mind?
twice?
Do you have like one you want to look at?
Yes, sir.
That's 6-1.
Yes, number 6.
All right, let's take a look at that one.
Yes, sir.
I'm going to share the screen for a moment. So let's see what we got going on here. It's integral e to the 7x. So this is 6-1 number 6. Integral e to the 7x sine 2x dx. All right. And now integration by parts is the product rule in reverse. This one's kind of an interesting one because this one has kind of a clever move to it. I'm going to let you, so the form is the integral of u dv is equal to u v minus integral of v du. That's the general format for integration by parts. I'm going to let u equals e to the 7x. Du is then 7e to the 7x. dv will be sine 2x. Integrate, that should give a negative 1/2 cos 2x. And again, I'm using the chain u to u to work that out. So what I get is I'm going to write the whole thing out. I get, so u and v come together. I get negative 1/2 e to the 7x cos 2x minus, and then the integral of these, now the 7 and the negative 1/2 come out, so I can put that out in front. I'm e to the 7x cos 2x dx. Okay. Now here's the deal. This one's got to be done with parts as well. So integration by parts again. So we've got a second run through. So I'm going to do the same thing. I'm going to let u equal e to the 7x. dv will be cos 2x. du is 7e to the 7x. v is going to be 1/2 sine 2x. So I've got to do it as well. And this is where it gets a little heavy. So remember, so keep this all in mind. I'm going to write this leading 7/2 is just hanging out in front. So I take the u and the v together. I've got 1/2 e to the 7x sine 2x minus the integral of v du. It's going to be these two guys. I'm going to bring the constants out in front. And I've got this. Now here's the thing. I'm going to write out the whole equation. I'm going to write this whole thing here. It's integral, the original integral was integral e to the 7x sine 2x. We got this term established. This, then I'm going to distribute the 7/2 through. It's going to become 7/4 e to the 7x sine 2x. Then I've got negative 49/4 e to the 7x sine 2x dx. Now check this out. This is kind of unique because this one is actually self-referencing. The same integrand reappears again. Okay, that's the trick on this one. The original integrand actually shows up again over here. So what we're going to do is we're going to algebraically isolate the integrand, or the integral, I should say. We're going to add this whole integral to the left side. So that this has a 1 in front of it. 1 plus 49/4 would be what? 53/4. These two things haven't changed. I'll just copy them. And then the last step is really easy. We just divide through by 53 over 4, or equivalently multiply by 4 over 53. And you can distribute that or keep it on the outside. It doesn't matter. Now, I kind of did that fast. I hope I did it right. You got to watch your arithmetic. You got to watch your negative signs. Every little step has to be correct. Okay. Now, in general, how do you know when to use the parts form? Well, again, through experimentation. There's really no other way to work this one out other than parts, because UDU is not going to get you anywhere. But sometimes you get something that looks like this. So, for example, moments ago I had x sine x squared, right? And that one was a UDU form. What if I just had x sine x? Well, you know what? That's not going to work as a UDU form. This will be a parts form, IBP. Now, how do you know that? Well, you know that through experimentation. You try it, you just try it. And if you can't get it to work one way, you try it another way. So in time, you start to become familiar with certain forms that just kind of trend one way or the other. There's just really no way, there's no algorithm that you can plug this into and it'll say, oh, use this form. You just have to kind of try it and get practice with it. I'll tell you what, since I've got that section up, 6-1, I'll refer to Erica's list there. She had 5, 6, and 14. This was number 6. Let me look at 14 since I've got it up there. Give me a second here. Okay, you know what? This is a good one. I'll tell you what, I'll just keep this up the way it is. For each of the following integrals, indicate whether integration by substitution or integration by parts is more appropriate, or if neither is appropriate, do not evaluate. So on this one right here, like I was just talking about, how about that? I must be psychic. It's integral x sine x. Well, one of the giveaways about parts integrals is that it's a product. But you'll notice that there's none of these is going to be a UDU. So in other words, you should try UDU first. And if you can't make it work with UDU, then parts is probably your next best choice. So I would say on this first one, definitely integration by parts. On the second one, unfortunately, it's a little small there. It's x on top, 1 over x squared on the bottom. That would be a UDU or substitution. That would be an LN form. The third one is integral x e to the x squared. This one will work out a substitution as well. U is x squared, du is 2x. You've got the x, so you're good to go. Number 4 is kind of like what we were discussing, is x cos x squared. This would work out by substitution. And number 5, I'm looking, substitution may not, well, actually, no, substitution will work because you can bring this up, 9x plus 1, and just treat it as the negative 1/2 power. And so let u equal 9x plus 1, du is just going to be 9 dx. You just need to put a 9 in the inside and a 1 over 9 on the outside. That'll actually work out real nice. Okay. So that one would be substitution as well. I'll do one more from this one. I just want to kind of, let me scroll here. Like this one right here, integral x e to the 4x. If you tried UDU and you let u equal 4x, then du is just 4. I got that extra x there, so that's not going to work. So this one would be a parts integral. This one would be a parts integral. In fact, it's kind of a cheat because this is all integration by parts. But if you try to do UDU on any of these, you're not going to get anywhere. Number 5 is kind of interesting. Let's look at that one because that one's just kind of a singular item, but it can still be done using parts. It's the integral arctan of 9 t dt. So this is number 5, 6.1. So again, the form is UdV, integral UdV is equal to uv minus integral of v du. So let's let u equal, well, we don't have much of a choice. It's got to be arctan of 9x or 9t. That means dv is dt. So then derivative of this is going to be 1 over, it's going to be 1 over 1 plus the 9t quantities squared. And then chain rule, put a 9 on top. V is t equal to t when you integrate. So when I sorry about that, I'm losing my train of thought here. So I take these two guys, put them together, so I get t times the arctan of 9t minus these two guys together, and it's going to be, I can pull the 9 out in front. This t will now be on top. This will be 1 plus 81t squared. Ah, this one will work just dandy. So this one will be a u to u. So again, just looking at the form here. If I let u equal 1 plus 81t squared, then du is going to be 162t dt. Well, there's my t in dt, so I'll just gently write in a 162, knowing full well it's going away here in about 2 seconds. But I got to balance it out here with 1 as well. So this one will, whoops, that. I'm just copying this guy, t times arctan 9t. And then let's see, we've got, this one's going to be an ln form. So it's going to be minus 9 over 162. This should reduce, this actually should reduce. I'm not going to worry about that. And then it's going to be natural log of 1 plus 81t squared plus c. I don't really care if you don't reduce your fractions. And that looks good. Ignore the scribble.
How did we get 162, sir?
What's that?
How did we get the 162?
Well, I looked at this and I said to myself, because again, I've been doing this for a long time. You'll get there too with practice. You got to look at this and just kind of say, hey, that looks like an ln.
Oh, it's squared. 81 is squared. That's
It's
why we get
81t squared.
Yes.
So I let u equal 1 plus 81t squared. I let u be the entire bottom here. Du is 6. Just take the derivative. 2 comes down, 162t dt. Well, there's your t and dt.
Oh,
And then I just need a 162. So I just kind of stick one in there. I don't care because it's going to go away. But I put its reciprocal on the outside to balance it. That's needed. The 162 on the denominator is needed. That survives. Okay. And that's how come that showed up. So we have a question here. I'm having some difficulty memorizing all the different integral and derivative formulas since many of them are very similar with small differences. Exactly. What level of rote memorization are we expected to have in this course? How would you recommend we focus our study? That's an excellent question. I hate to tell you this, you just got to practice a whole bunch of them because what you're doing now is you're getting a very heavy dose of integration where the integrands are deliberately similar in appearance, and there are minor differences, and we've gone through a couple of them in class or in this session already, where just the presence of an extra exponent or an extra variable can make all the difference. And there's no, like I said, there's no formulaic way to just say, well, this one automatically is done using parts, or this one's automatically done using substitution, etc. A lot of it comes down to just exposure and practice. So at first, there is some rote memorization, but with practice, it becomes more natural. That's what I'm hoping for. You won't always be just rote memorizing these things without context. At first, that's kind of necessary, but I hope that you do enough of these that it starts to kind of click. That's my hope. It might take you a half dozen, maybe 10 of them before you start to see these subtle differences. Okay, I guess the analog is if you were in a biology class, and you have two molecules that look almost identical, but one's got an extra, oxygen, hydrogen thing stuck to the end of it. It's a totally different chemical at that point. To the untrained eye, they look the same. But to a biologist or a chemist, they would say, oh, I know what that is. Same here. You know, I can see these because I've been doing this for a while, and I can just immediately tell what form it is. But I understand that you are all kind of on that steep learning curve where you're learning how to recognize. So this is where you're getting that experience, and the best way to do it is just to do as many of these as you can. And if you need more practice, I don't know if you guys have a copy of the textbook, but the textbook has all sorts of good examples or good problems to work on where you can check yourself with the key, or you can just always Google, you know, I need practice on integration by parts and see what pops up. And there's always a lot of good sites out there. So there's you know, just wherever you can get the problems, doesn't matter to me as long as you do them honestly. All right, we're doing good here. We got about 20 minutes.
So like
Go ahead.
one of the videos did the indefinite integral of secant squared x tan x dx. And I think that helps me understand kind of what you were saying, because when I went to solve it, I didn't solve it with u being tan x. I solved it with it being secant x. And then that video went and did it both ways and showed us like how it could, even when you're doing it, you could get different answers, but we're just manipulating the problems to get something that's compatible with the equation that we're trying to do. So,
you know, this one is actually kind of fun because you actually get different looking answers, but you actually get the same answer.
Yeah, I thought I had it all wrong. And then he went on to the second part of the video, and then he showed how you could have done it this way too. And then I realized, like, oh, they're the same, but I didn't naturally see that equivalent in my head. I just thought I had it wrong first.
Check this out. They're both U to U forms. In the first form, your answer is going to be, they're all balanced. It's ready to go. It's just going to be 1/2 secant squared x plus c. This guy over here is going to be 1/2 tan squared x plus c. And you're going to think to yourself, I did it wrong. It's supposed to be this guy or whatever. You think it's wrong. But you know what? They're actually the same. You know why? Check this out. Because you can use that Pythagorean identity. Remember, secant squared is tan squared plus 1. If you distribute the 1/2 in, you get a 1/2 plus c. But you know what? You just blob the 1/2 and the c together as c. So you actually get the same answer. So this is a good example. There's a lot of good examples in here. You know, I don't know. I kind of view these as puzzles. You know, because when I do these, trust me, I don't look at these beforehand. I'm just as surprised as you are when I see the question pop up. And immediately I have to kick into gear and I have to think, all right, how do you do this one? What's the form I'm looking for? There was one on Infinity, on Ed discussions that somebody posted, and I put an answer to it. And I'll be honest, it took me about 10 minutes to work that one out. Take a look at it when you have a chance. And but yeah, sometimes you just gotta wrestle with it. And if anything, what you're going to get out of this, you're just going to become better overall at your trig, at your algebra, at your recognition skills. This is going to do well for you as you go higher up in your mathematics. All right.
I have a question for you. It's kind of, I think it's a me problem. Well, I'm sure it's not just a me problem, but I think I already know your answer,
Uh-huh.
but I'm having trouble recognizing, like when you're doing integration by parts, like when you need a second integration by parts or a substitution instead. So like you'll get the one problem, you'll start working through it, and then I'm having trouble recognizing where that second one needs to then be integrated.
I did one. You know what? I did the one moments ago where it self-referenced itself. There's also cases what are called nested parts. I'll just make one up. Give me a second here. I got to think this one out. usually something like x to the fourth e to the 3x. If you do this with integration by parts, I would make my first pass u is x to the fourth, du is 4x cubed, dv is e to the 3x, so v is 1/3 e to the 3x. And I would have u and v, so that gives me 1/3 x to the fourth e to the 3x minus the integral of v to u, which is going to be, I'll pull the 4 out, it's going to be x to the third. Actually, the 4/3 will come out, my bad. It'll be x to the third e to the 3x dx. And you know what? This is actually correct. You've actually reduced the power by 1, but you know what? You got to do integration by parts again. And and then eventually you'll get it down to x squared. You don't have to do it again. And if you work this out the long way, it's going to take you a long time. It's going to probably take you 20 minutes. It's going to take up the whole length of the page, and it's going to be a nightmare. So in a case like this, there's actually a really nifty trick. This is called tabular integration by parts. I'm going to show this to you. This works out real nice when one of the terms is polynomial. So what you do is you make 2 columns, and you take the polynomial term and you differentiate it all the way down to 0. You got to take it all the way to 0. So those are derivatives. So I did derivatives. Meanwhile, I'm going to anti-derive the other column. So this is going to be 1/3 e to the 3x. This will be 1/9 e to the 3x. This will be 1/27 e to the 3x. Every time multiplying by 3. Okay. And then what you do, this is real cool. You draw diagonals from the upper left, just going down one notch. And you alternate the signs. And then you just read them off. It's going to be these two multiplied, so 1/3 x e to the 3x. And then it's going to be minus these two multiplied, so it's going to be -4/9. Actually, it should be x to the fourth e to the 3x. This will be -4/9 x cubed e to the 3x. This will be 12/27 x squared e to the 3x. This will be -24/81, which I think reduces, but I'm not going to worry about that. X e to the 3x. And this will be +24/243. And that should also reduce, but again, that's not really of concern. And boom, you're done. So this is kind of nifty to help you with these nested parts cases. But it only works when one of the parts has to be polynomial, so you can take its derivative down to 0. If you don't have polynomial, like the one where we had e to the 7x and sine of 2x, unfortunately, those don't differentiate to 0. So that wouldn't have worked on that one. But this one, it worked out beautifully. And I don't really care if you don't reduce your fractions. That one reduces. The last 3 fractions reduce, but it's not really that much of a bother, as long as you get it right.
Hey, Professor,
Uh-huh.
if we're done with this topic, it would be I had some questions on 6.2, and it's not really so much questions, but I was wondering if you could just go over some of the I think they're called the reverse substitutions with where you sub a trigonometry function into uh one of the other equations, like 6.2, either 13, 14, or 15, any of those.
All right, give me a second here. Just bringing it up. All right, so yeah, let's take a look at some of these. I'm going to share the screen. Which one looks fun? Um, let's take a look at, how about this one right here? This is 6.2, number 15. is the integral -10 on top, rad x squared plus 16 on the bottom. Now, we just got done talking about, forms here. What if there was an x on top? In that case, this would just be a simple u to u substitution. Boom, 2 steps, you're done. Unfortunately, there's no x there. The radical is going to be a problem here. This one's going to require a trigonometric substitution. So here's what I do. Over here on the right side, I'm going to write the Pythagorean identity. And then I'm going to divide through by cosine. I'm going to get the alternative form. And then there's also another form where I bring the 1 over. I'm leaving off the x's. I'm just trying to get a quickie. Sorry about the blurriness. And I look at the form here and I go, which one looks most like this? Actually, this one right here. Because I've got something plus squared. So what I'm going to do here, I need to make a judicious substitution here. I'm going to let x equal 4 tangent theta. That means dx is going to be 4 secant squared theta d theta. My bad, d theta. And then when I make the substitution here into the radical, check this out. I'm going to get 4 tan theta quantity squared plus 16. That means when I square it, I get the 16 tan squared theta plus 16. That means I can factor out the 16. And I get tan squared plus 1. Should be a theta there. That means I really have radical 16, and then tan squared plus 1 is actually secant squared. And I have actually created an integrand that's a perfect square. So I can get rid of the radical. And so what I do now is I come back to my integral. I'm going to pull the -10 out in front. dx is this guy right here. It's the 4 secant squared theta d theta. This whole thing right here, the radical part, worked out to be 4 secant theta. Just boom, like that. And the beauty of this is now the 4's cancel, one of the secants cancels. You just got the integral secant theta d theta. Okay, this allows us to get rid of the radical. This particular form is one you probably would have seen it in Calc 1. I'm just going to go ahead and write it. It's going to be -10. -10 is just going on for the ride. It's going to be -10 natural log secant theta plus tan theta. And I'll just put in parentheses from Calc 1. You probably would have seen that. If not, well, you're seeing it now. So I was able to turn this thing into something with theta utilizing trig identities. It got rid of the radical, which was really what I was after. I simplified, I integrated. Now that's my answer, but unfortunately it's in the wrong variable. So what I need to do is I need to go back to the original substitution here. I'm going to draw a right triangle. And I'm going to say to myself, x was 4 tan theta. That means x over 4 is tan theta. And if I just tuck a theta into one of the corners here, tan is always opposite over adjacent. That means the Pythagorean theorem gives me the hypotenuse. Okay. And then I just read off what I want. So it's going to be -10 natural log. Secant is going to be, it's the inverse of the cosine. So cosine would be adjacent over hypotenuse. So secant is just the other way. It's going to be hypotenuse over adjacent. And then the tangent is just opposite over adjacent. And you get that. Now here's the thing. You check your answer. This is correct. But then you check your answer and all you see is this. So if you tried Wolfram alpha, for example, you would see that. What happened to those fours? Well, what happened was you actually have a common denominator here. But then you can split, and again, the negative 10 is just hanging out. It's not doing anything special. It's the different, the log of a quotient is the difference of the logs. And then when you distribute your negative 10 through, the negative 10 times this guy gives you what you see right here. The negative 10 times the ln4 is just a constant. You actually have positive 10 at ln4 plus c, which we just simply smush together into plus c. So that's where the over 4 went. If you had left these in, it wouldn't make a difference. Ironically, you could put any number down here as long as it's the same, and it would still be correct. Okay.
Now, in scenarios like that, like if on, say, on like the test, if we left it as x squared plus 16 over 4 plus x over 4,
it'd be correct.
okay.
Yeah, that kind of thing, because you know the way you check it is you just graph it, and the graphs match up, they work. So it's basically doing like a graph check. What I want you guys to be aware of is if you are looking this up, let's say you try on Wolfram Alpha to check your math and you don't see that over 4, don't freak out. Doesn't mean you did it wrong. Just show you what happened with the algebra. All right. We got time for maybe one more question. Anybody want to? We did a good, yeah, go ahead.
Are there any of them on there where you have to do like the u and then the w, and you're actually solving the definite integral? So then we're changing the values of a and b in the function.
Oh yeah, there were in the yes. I avoided those. What you can do is you can always just ignore the bounds and then do the integration, put it back in the original variable, and then just employ the bounds again. So I'll end up with one. I'll just show you kind of an easy one. Actually, no, I saw one. If you give me a second here. Hold on. Like number 14, for example. If I were to work this one out, and this one would work out with the trig sub, I would actually just ignore the 0 and the 3/2. I would just work this out, doing all the work to get it all the way into theta temporarily, and then I would convert it back into x, and then I would put back on the bounds. I personally don't think it saves you much time to make the bound switch early on, although you can. To me, I always figured that 99% of the battle here is working out the integral and the antiderivative. And then once you've got the antiderivative worked out, then pop in your numbers. So just kind of ignore these for a while. That's my feeling, at least. Let me see what else. Like this one right here, I would work this one out. Number 11 here. This one would, oh, you could probably get away with doing parts. If you treat this x cubed as x squared times x. But again, I would not even worry about the bounds until the very, very end. Because to me, I don't know. I find them to be kind of intrusive until I get everything figured out. But that's just me. It's up to you. I'll tell you right now, and I'll just straight up tell you, you can cheat on these because you can just simply feed these into a calculator and Infinity will accept it. So that we know that. We're well aware of that. So typically on the exam, all you're going to see are indefinite forms. Okay. Well, guys, I'm going to go ahead and power down here. This will be available. I'll send a link It'll probably be about an hour before I get it ready. I'll send a link and you'll be able to view it and relive the experience. So I appreciate you all showing up. And again, I'll do this about once a week, generally on Sundays. I understand that you guys are probably all over the different parts of the world and can't make it conveniently. And we had that time change recently too. So the Arizona, we're now back in line with the West Coast. So it's confusing, but I think we got it figured out. All right. Cheers. 5, 4, 3, 2, 1.